He knows it's a joke.
I do try my best to ask questions sometimes. But sometimes I'm not going to ask them really dumb questions that I just made up.
What's today, the 12th?
Yes.
That guy in the front will. Yeah. Who's that?
Here you go.
I don't even know who you're from. There you go, Spencer. I do.
All right, let me begin with a word of prayer. So, dear Heavenly Father, we thank you again for your many blessings to us. I pray for you that we'd glorify what we do. Pray that we would understand a little bit more about linear algebra today, and just please give us understanding today, Lord. In your name I pray, Lord Jesus. Amen.
Amen.
All right, so yeah, I don't know what's wrong with me. Like last time, I thought I had to teach like all the material for yesterday and today and Monday, which is why I was frustrated, like duh. So yeah, we've still got like 2 more days to understand QR decomposition and least squares, so you know, no need to do everything at once. So that's why I didn't make a video, because we're not actually behind. So let me do an example of Graham-Schmidt. So let's run the Graham-Schmidt on, let us do it on the set 0, 1, 1, 0, 1, 1, 1, 1, and 3, minus 2, 0, 1. All right. So I'm going to do the unnormalized Graham-Schmidt, so I'm not going to normalize as I go. So here goes. So first of all, u1 prime, I'm just going to say is the first vector. So by the way, the first time I did this calculation, I had the the vectors such that the 1, 1, 1 vector was first, and it just, no matter how many times I do it, I can't get it to work out. And it's just dumb because it's just arithmetic. But I think maybe this is an important thing to do, which is if you've got a really sparse vector, like a vector with like a lot of zeros, put it first, you know? Like you don't have to leave the order of the vectors the same. Like you can change the order of your initial set of vectors and kind of go from there. That might save you a lot of calculation. Like if you've got a vector with a lot to it, maybe it makes more sense to shift it to the end, you know? Anyway, there's u1 prime. That's it. Just declaring that. u2 prime, what we do is we take the 1, 1, 1 vector and we subtract, let's see here, we subtract the 1, 1, 1 vector dot previous one divided by the dot product of that with itself, which of course you probably could safely just write down, but I say that as a person who, it seems like it takes me like 3 attempts to get this correct. Even when it's just 3 vectors, I'm just bad. I honestly, just full disclosure, I'm bad at Graham-Schmidt. I hope you guys can get better than I am. Shouldn't be hard. So, I mean, it definitely shouldn't be hard on the take-home part of the test, right? Anyway, what do you got here? You've got 2, 1 plus 1, and downstairs you got 2. So you got, whoa, dude, that ain't right. I'm just getting 0, because that's like 1. What did I do? So what's the rule? For example, u2 prime is supposed to be like v2, let's say, minus v2 dot u1 prime divided by u1 prime dot u1 prime times u1 prime. Notice that's U1 prime, not, so my V, this is my V2. True to my word, I found a way to mess up Gram-Schmidt. As you can see, this is supposed to be what? It's supposed to be the, this guy here. Excuse me, the 0, 1, 1. 0, 1, 1, 0 is what's supposed to go there. And we can check as we go, right? At every step, you should check, is the next one you're producing perpendicular to all the ones that came before it? Because if it's not, you've done it wrong. This fraction right here works out to 2 over 2, also known as 1. And as such, we just get what? 1, 0, 0, 1. Right? Is the dot product of, you know, a quick sanity check here, u1 prime dot u2 prime equals 0? Hooray! All right, what's up next? U3 prime, right? So what's the formula for U3 prime? I'll write it up here. So this is unnormalized Gram-Schmidt. U3 prime is V3 minus V3 dot U1 prime divided by, let me just call it what it is, the length of U1 prime squared times U1 prime minus V3 dot U2 prime divided by the length of U2 prime squared times U2 prime. All right? And let's see here, how's that go? So we've got our 3 minus 2, 0, 1 vector. And then I do what? V3 dot U prime. So I do 3 minus 2, 0, 1 dotted, and then 3 minus 2, 0, 1 dotted. So the first dot is with my U1 prime, which is 0, 1, 1, 0, divided by 2. And then this one, 1, 0, 0, oopsie, I made a mistake again, divided by 2 times 1, 0, 0, 1. You guys tell me my mistake. It's fairly obvious. I've got vector minus number minus vector. So no, I'm missing something in the middle term. What am I missing? Right here, I'm supposed to have a, oh yeah, you're right. Let me, thank you. I do have a name for it, don't I? I can fit that in here, can't I? So U1 prime, thank you. Okay, so what is that? This right here, man, that is the 3, so 3 times 0 minus 2 times 1 plus 0 times 1 plus 1 times 0. So we get a net of minus a minus 2, which is 2 over 2. I believe that this works out to altogether, including the minus, a 1. And the other one, we've got 3 plus, so this works out to 2 over 2. So this works out to 1. With it, well, if I'm including the minus 1. I mean, you got to be careful about the signs. That's what will get you wrong here. All right, so if I haven't done something stupid, let me just write it down here. So I've got 3 minus 2, 0, 1, plus U1 prime, which was 0, 1, 1, 0, and then minus 1, 0, 0, 1. So U3 prime, apparently, if I haven't done something stupid, which is to be seen, looks like I've got 2 minus 1, 1, 0? Oh, that feels wrong. Just a second, let me think about my life.
I think it might be
Yeah.
the dot product. The 3 minus 201 dot with 1201. I think that should be 4 in the new one.
4 and 4 divided by 2?
Which is a
2, so minus 2 overall, right? Because this minus here, which makes this a 2 and a 2, which gives us 1, minus 1, and then, let's see here, 1, and then 1 minus 2 is minus 1. Good, yeah, that's what I got yesterday. So, there you go. And you can check, you can easily check that U3 prime dot U2 prime equals to 0, and U3 prime dot U1 prime equals to 0. So, yay! And like on the final exam when I have you Gram-Schmidt 3 things, don't just write down dot product and put a check without actually checking, because it's not smart. Like, you should actually check if you're going to check, you know? Don't be like me sometimes. So, but that you can see it though, right? That this is perpendicular to both that and that, because you get minus 1 plus 1 and 1 minus 1, both of which being 0. All right, so there we go. Now we have, if I call this set, I don't know, S, right? Then, to summarize, we can take S and then run Gram-Schmidt, right? And out pops the following orthonormal set. Now I need to normalize, right? So I have like 1 over the square root of 2, right? 1 over the square root of 2, 0, 1, 1, 0. And then how do I normalize U2? Oh, 1 over the square root of 2, 1, 0, 0, 1. And then what's the length of U3 prime? Square root of 1 squared plus 2, 1 squared plus 1 squared plus 1 squared. Square root of 4, also known as 2. So we divide by the length, which is 2. So normalizing, 1 minus 1, 1 minus 1. All right, there we go. So there you go. This is an orthonormal set. All right. Are we good? So I wanted to give you an example of Gram-Schmidt with 3 things that's completely worked out, and it's a little bit non-trivial. I think this does that. Now, let's talk about the QR decomposition. So here's how it goes. If A is equal to, let's say, A1, A2, dot, 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 AK, where the rank of A is equal to K. So what am I saying? That's another way of saying that the columns of K are linearly independent. Okay, so suppose you have K linearly independent columns, right? And, you know, for context, A could be an element of like R M by K. Okay? So it doesn't have to be a square matrix. So then the thing is, we can we can take the set of columns, right, AK, and run Gram-Schmidt and normalize to, and I'll use the, so like the Lay likes to use U1, U2, dot, 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 UK for these. Now he uses X's for the columns. I can't do that. That's just weird. I'm going to use A1 through AK for the columns. I hope you can forgive me for that departure from the book notation. But so this is a orthonormal basis for the column space of A. All right, the column space of A, it's the span of the columns of A, right? So you can run Gram-Schmidt on the set of column vectors, and if they're linearly independent, and we can do more than that though. Like how does Gram-Schmidt work? The standard algorithm, what does it do for us? Notice that the span of, let's say, A1 through AJ is equal to the span of U1 through UJ for the standard Gram-Schmidt. All right. Now there I would get into trouble if I did that thing I said at the start of lecture about switching the vectors around to make it easier. If I do that, it's going to ruin this. All right. So, all right. You see what I'm saying? Like if I have the particular ordering of the vectors given in the column, I can't just willy-nilly change those around and hope that this is true. See, what this is saying is that, and it's pretty obvious at the start, right? Is the span of the first vector the span of, like, if V1 is A1, is the span of A1 the same as the span of U1? Notice that U1, my notation here, is just that, just to be clear here, guys, U sub j is equal to 1 over the length of U sub j prime times U sub j prime. So it's just the normalized U sub j prime. Yeah? So it's fairly obvious if you sit and look at these formulas that the span, anyway, you can prove that this is true for the standard Gram-Schmidt algorithm. But I probably wouldn't ask you to do that. I don't know. Is that a reasonable question? Well, let me just say this. To see that this is true, it is fairly easy to demonstrate that, that you can write U primes as linear combinations of the A's from before. Like, for example, for this one, see this one here? In our current situation, we'd have like we'd have U2 prime, right? Equals to A2 minus A2 dot U1 prime divided by the length of U1 prime squared U1 prime. And so you can see that that A2 is an element of the span of like U1 prime, U2 prime, because you can solve that for a linear combination for A2, right? And here's a question for you. If you take a spanning set, right, and you say normalize, like it's a simple thing to see that this is going to be straight up equal to the span of like U1, U2 if we normalize those vectors. Like normalizing the vectors doesn't change the span at all because it would just redefine the constants by like a multiple if anything you could reach by linear combination with the the unnormalized vectors, you can reach by the same, almost the same linear combination with the normalized vectors. So anyway, let me not belabor this. I think it's fairly obvious that this is true for the Gram-Schmidt algorithm. For a modified Gram-Schmidt, I don't know. Modified Gram-Schmidt, I'd be leery, okay? But for Gram-Schmidt, this is true. So what I'm trying to say is that the QR decomposition, it is assuming that you're going through usual Gram-Schmidt on the column space. And if you do that, something really cool happens. I'll show you here. So suppose we have that, right? What does this mean? This means that we can write, goodness gracious, a sub j, right, as equal to, let's say, a sub j dot u1 plus a sub j dot u2 plus dot 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 plus a sub j dot uj. Why can I do that? So AJ is in this set, right? This is an orthonormal set, which means it's a basis for these guys, right? And if it's a basis, then we can write anything as a linear combination of the basis elements and the components. The components with respect to the orthonormal basis are just given by dot products, like we proved the other day, right? Simple as that. But we could write this a different way, right? We could write this like, let's see here. I think I might as well, yeah. So if you look at this, we could also write this as what, like u1, u2, dot 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 dot, uj, right? And I guess we could just keep going, right? We could just keep going, couldn't we? uj plus 1, all the way on out. How many do we got? U sub k, right? So how many u1s do we want? We want a sub j dot u1 of those. We want a sub j dot u2 of those, and so forth and so on, until we get to a sub j dot uj, and then we got zeros down here. So let me write it out. We have A, of course, is A1, A2, dot dot to AK, right? And so we've got A1. So to put this more succinctly, we can call this big matrix here U, right? And so for the first one, we've got U times just, this just stops at 1 for the first one. So like for j equals to 1, it's just non-zero at the top and everything else is 0 below. Yeah, so it's just like A1 dot U1. And then zeros. All right, that's my first column. And then I've got U times A1 dot U1, A2 dot U2, and then zeros. Let me put a different color for my column separators here. I'll put these in purple. See them better. All right, and then you have u times a1 dot u1, a2 dot u2, a3 dot u3, then zeros, right? Oh, wait a minute. Oh, look at that. Am I right? No. What's the pattern? Was it different A's at different levels here? No, it's always just A sub j. So help me out here. This should have just been what? 2 and 2, right? And this should have been 3, 3, 3. There we go. And this goes on. This goes on until finally we get to the last one where we've got, you know, ak dot u1 and all the way down to ak dot uk, right? Finally, there's no zeros because it's uk. How big is u? How big is u? This is a. Oh, I'm an idiot. Look at this. Come on, guys. Don't let me do that. What's that? Excuse me. That is a k. Yes. There we go. So this is, and each one of these is an RM vector. So we're looking at an m by k matrix here. That's what U is. Yeah. Now, can we rewrite this? Oh, and I'm an idiot. We don't usually call this U. I have to fix this, guys. This U was supposed to be a, it's kind of important. Q. This is the Q. Oh, man. So it goes. Oh, wait a minute. Maybe I'm wrong. Hold on. Flag on the play. Wait. Ay. So, all right, this, we can factor the U out. And then we've got, you know, A1 dot U1, and then A2 dot U1, A2 dot U2, and so forth, and then zeros. AK dot U1, AK dot U2, AK dot UK. But we can write, notice that we can write like A sub j dot, let's say, U sub I is what? That is U sub I transpose times AJ, right? And as such, I'll put us out of our misery here. You can write that as U transpose times the matrix A1, goodness gracious, A2. Oh man, seriously? Oh. No. I was right. This is supposed to be Q. That was supposed to be Q. I was like, this feels wrong. It felt wrong because we were done. So I'm trying to snatch defeat from the jaws of victory here. Dummy. Me, not you. That's Q. And this, my friends, is R. R is an upper triangular matrix. And when you study the you can arrange it so that all of these entries are positive. So it's this, upper triangular with positive diagonal entries. Now it doesn't. There's a possibility that if you ran Gram-Schmidt in a, well, I wouldn't say incorrect way, but it's potentially possible that you end up with like a negative number here, he says in the book. But if that happens, you can just basically go back to your Gram-Schmidt and like trade out the vector that you had for minus it. Think about this. If if these vectors are all pairwise perpendicular, right? Going back to my example, it is still true. Like you could take any of these and replace them by minus what's there. Still works, right? That essentially corresponds to the freedom to redefine you can redefine the U1 through UK, and as such, you can force these to be positive. And that's what's done in the standard QR decomposition. Now, why is this interesting? Because Q, goodness gracious. So Q is what happens when we multiply, say, Q transpose times Q. What's that equal to? So Q was what, M by K? So Q transpose is what? So K by M, M by K, right? And if you calculate the ijth component of this, what do you got? You've got Ui dot Uj is what you got, right? But that is, by construction, Kronecker delta Ij. So in other words, this matrix Q times that is equal to the K by K identity matrix. It's an orthogonal matrix. Those are super nice because what's their inverse? Transpose. On the flip side though, well, excuse me, I've said too much. Is Q an orthogonal matrix? The answer is no, not always. Because on the flip side of things, when we do Q times Q transpose, that's a what? That's a M by K times K by M, right? And what's that work out to? I don't know, but it's not the M by M identity, right? Because M, question, what's the relation of M and K here? Think about this. Can M be less than K? Search your heart. So notice that the M has to be greater than or equal to K. That is forced upon us because we're assuming linear independence. If I had only 2 rows to work with, I can't get 3 linearly independent columns using 2 vectors. You can have at most M linearly independent vectors in Rm. So that puts the upper bound on K of just M. So anyway, this is an M by N matrix, and that doesn't have to be the identity matrix, but what that is a projection matrix like we talked about last time. That actually is the projection matrix that we were talking about. Let me try to flesh that out for you. So, all right. Uh-oh. Let's see here. So we're going to remember that. Come on. So general comment, if W is equal to the span of U1 through UK, right? Suppose that and let's suppose that this is an orthonormal basis. As I described last class, the projection onto W of a vector x is given by like U1 dot x times U1 plus U2 dot, I mean, I could put the x first or last, doesn't matter, dot product's commutative, right? UK dot x, UK, what is this? This is the matrix U1, U2, UK times, yowzers, U1 transpose x, U2 transpose x, UK transpose x. But that's exactly U transpose times x. So you see the standard matrix, well, standard matrix. Anyway, this is, I shouldn't say that, perhaps, but this is a matrix which does the job of the projection. Excuse me. I was stuck on this last class for some reason. I don't know why. Now, let's put this all together. Let's actually find the QR decomposition for the matrix that has these as its columns. Yeah, we can do that. So, so circling back to my example 1, we can look at the matrix A, which is equal to, 0, 1, 1, 0, 1, 1, 1, 1, 3, minus 2, 0, 1, right? We know that the set of vectors I have on the middle board form a orthonormal basis for the column space of A. So we have U equal to 1 over root 2. Oh, let me write it out. Oh, it's ugly, but let me do it. I gotta do it. So I'll write the matrix. So I'm going to write the basis, the matrix for that set. So it's a what? A what by what? It's a 4 by 3. So we've got 0, 1 over root 2, 1 over root 2, 0, 1 over root 2, 0, 0, 1 over root 2. And last but not least here, hey glasses, 1 over 2, 1 over 2, minus 1 over 2, 1 over 2, minus 1 over 2. There you go. How do you calculate? So like I went through this derivation, right? Somewhat slowly and painfully. My apologies. Let me just erase, let me put this up here. I'm going to save this up here. I need to erase it though. So we got projection. Really we could say projection onto the column space of A in our current context of X is equal to U transpose X for what it's worth. Here we've got, U is orthonormal basis for column space of A. All right, there we go. So you guys tell me, what is a practical method to calculate the R if you don't want to like try to slavishly sort through my formulas. Like let's look at it. We've derived the following relation that A is equal to QR, right? And I keep forgetting this is Q. All right, there we go. This is Q. So how do I find R? So the answer to the unanswered question over here was a projection matrix. It's a projection matrix onto the span of Q. It's a projection matrix onto the span of, what's this? Not the span of Q. I should say it's the span of the name of the. It's this. Well, for this context, it's the span of the A1 through AKs, right? Oh no. Okay, so how do you solve for R? What if we just multiply both sides by Q transpose, yeah? So we've got Q transpose A is Q transpose QR, but Q transpose Q is just the identity, right? It's the K by K identity, which is just R again. So we can figure out what R is simply by multiplying A by the transpose of Q. So R is equal to Q transpose, which is simply 0, 1 over root 2, 1 over root 2, 0, 1 over root 2, 0, 0, 1 over root 2, 1 half, minus 1 half, 1 half, minus 1 half. So I got to take that 3 by 4 matrix, multiply it by my 4 by 3A, 0, 1, 3, 1, 1, 0, 1, 1, 1, 3 minus 2, 0, 1. All right. So what's my R? All right. What I calculated. Whoa. Dude. Oh yeah. So I got root 2, minus root 2, 0, root 2, 2 root 2, and 0, 0, 2. So you can check that A is equal to Q times that R, right? You can start to see why that's true. I mean, imagine taking the first column in R, multiplying over here, you get what? 0. Root 2 over root 2, also known as 1. 1, 0. So I get 0, 1, 1 for the first column of A. Multiply the second column of R times Q. You get 1, 1, 1, 1. Third column, I get root 2 minus 3 root 2. Excuse me, my bad. Well anyway, you can check, I've checked it, okay? It works, yeah. Agree? Disagree? Who cares? Right? Wonderful, you found a way to decompose a matrix as an orthogonal matrix times this upper triangular matrix. Who cares? What does it do? What's its point? What's the point of all this? Let me show you. Well, I'm not sure we're going to get to the point of fully appreciating why this is so really, really neat. I mean, anytime you have a way of taking a matrix apart into a standard form, it yields itself to certain arguments. That is always going to be true. I need to circle back here. And talk to you guys about the main, finding projections onto subspaces is neat, obviously. It's a neat thing to be able to generalize the concept of a normal vector to a three-dimensional subset of R5 or something. How do you find both of the normal vectors? Uh-oh. But the main application that I have in mind for this course, for this material, is what's called least squares. So here's the problem. You're given AX equals to B, but B is not an element of the column space of A. What does that mean? If B is not an element of the column space of A, what's that mean? That means that you cannot solve the equation. It's an inconsistent equation. So what we do is we say, okay, well, I can't solve it. How to minimize the AX minus B, right? So that would be basically the error term, right? If I call that the error term, I want to make that as small as possible. All right? It turns out, I'll explain this, I don't want to rush it, I'm just going to tell you the answer and show you what QR means for it. It turns out that the solution to A transpose AX equals to A transpose B, this solution, X solving that, minimizes that. So you don't solve the equation. You take the equation you're given, you multiply by the transpose of the coefficient matrix. That gives you the best approximate solution. Isn't that messed up? Like, how could it be that simple? But what does this look like? If we take the QR decomposition, what's this look like? You got yourself a Q, an R, you transpose it. And then you got yourself a Q, an R times X. And you've got a Q and an R transpose times B. What's that work out to? You got yourself R transpose Q transpose Q R X equals to R transpose Q transpose B. But Q transpose Q is what? It's the identity, right? So this gives us R transpose Rx equals to R transpose Q transpose B. But this implies actually that Rx has to be equal to Q transpose B. This is easier to solve than A transpose AX equals to B, A transpose B. Possibly. Why is it easier to solve? What is R?
Upper triangular?
Do you remember solving systems of equations with upper triangular coefficient matrices? Maybe you don't, because you didn't suffer. Those were so easy, you just did them, right? Like, you literally just solve the top equation, the bottom equation, and back substitute, done. You don't even need to do you don't even do row reduction for these. You just solve by substitution straight up. So that's where the QR decomposition really shines, is it gives an elegant method to solve the least squares problem, which I'll have to explain next class. So, thanks guys.